Introduction to Fortigate HA. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are covering Fortigate high availability design across on-premises data centers and all three major public clouds, AWS, Azure, and Google Cloud. High availability, or HA, is the discipline of engineering a firewall deployment so that the failure of a single device, a single link, or a single power supply does not interrupt traffic. For a security appliance sitting inline between users and applications, this is not a nice to have. If the firewall stops forwarding, the business stops working. We will begin with the foundation. We will cover what HA actually means for Fortigate, the two operating modes Fortigate supports, the Fortigate clustering protocol that glues the cluster together, heartbeat interfaces, session synchronization, failover behavior, the physical topology you would build in a data center, and the CLI commands used to configure it. Once we have these fundamentals solid, we will take the same concepts and apply them to each public cloud, where the physical constructs we rely on premises simply do not exist and we have to use different mechanisms to achieve the same outcome. This content is aimed at network engineers, security engineers, and cloud architects who need to design resilient Fortigate deployments. I will assume you have a working understanding of firewalls, Layer 2 and Layer 3 networking, and basic cloud concepts, but I will not assume any prior Fortigate HA experience. High availability modes: active passive and active active. Fortigate supports two HA modes, and the choice between them has real implications for traffic flow, capacity, and troubleshooting. Let me walk you through both. Active passive, often written as AP, is the default and by far the most common deployment. In AP mode, two or more Fortigates form a cluster. One device is elected as the primary and actively forwards all traffic, and the other devices are secondaries that sit idle. The secondaries synchronize configuration and session state from the primary, and they monitor the primary through heartbeat packets. If the primary fails, one secondary is promoted to primary and takes over forwarding. The failover is typically sub-second for link-level failures and a few seconds for full device failures. Active-active, or A-A, is the less common mode. In A-A, all devices in the cluster forward traffic simultaneously. The primary still owns the management plane and still receives all traffic from the network, but it load balances specific session types, primarily UTM-inspected sessions like antivirus and web filtering, across the secondaries for inspection. The result is that CPU-intensive inspection work is spread across multiple devices, but the primary is still the single ingress and egress point for the cluster. This is important. A-A does not double your throughput for all traffic. It specifically helps when UTM inspection is the bottleneck. Let me walk through the diagram. It shows a comparison of the two modes. On one side we have AP mode where the primary Fortigate is actively forwarding traffic and the connection from the primary going to the internal network is labeled active traffic, meaning all real user sessions flow through this device. The secondary Fortigate receives no user traffic and is labeled idle. There is a bidirectional link between the two devices labeled heartbeat and sync, which represents the HA control traffic and session synchronization flowing between them. On the other side we see AA mode. The primary Fortigate again receives all traffic from the network, but this time the primary forwards some sessions internally to the secondary for inspection. This is shown by the link from primary to secondary labeled inspection offload. The secondary processes those offloaded sessions and returns them, and the primary still handles the forwarding back to the network. The same heartbeat and sync link exists between the devices. The key takeaway is that in AA both devices do work, but the primary remains the single entry and exit point. For most deployments I recommend a /P. It is simpler to reason about, troubleshoot, and size for. A/A is useful when you are CPU bound on UTM features and cannot scale up to a bigger platform, but it has more moving parts and some limitations around features like asymmetric routing handling. Cluster rules and the election process. In any FGCP cluster, at any moment, exactly one device is the primary and the others are secondaries. The election process determines which device wins the primary role, and it runs both at cluster formation time and any time the current primary becomes unreachable. Let me walk through this sequence diagram. The diagram shows the election conversation between two FortiGates at cluster startup. Both devices power on and begin sending hello packets on the heartbeat interface. Fortigate A sends a hello to Fortigate B announcing its candidacy, including its override setting, its priority value, its monitored port status, its uptime, and its serial number. Fortigate B sends an equivalent hello back to Fortigate A with its own values. Both devices now have each other's election criteria. They independently run the same comparison logic. Both devices conclude that Fortigate A wins the election and should be primary. Fortigate A sends a confirmation announcing itself as primary. Fortigate B acknowledges and assumes the secondary role. Fortigate B begins pulling configuration from Fortigate A to synchronize. Fortigate A confirms configuration sync is complete. The cluster is now operational with Fortigate A as primary and Fortigate B as secondary. The election criteria are evaluated in a strict order, and the first criterion that produces a difference decides the election. The first criterion is override status, which is a per-device setting that says whether this device can preempt a healthy primary when it comes back online. The second is monitored port status, meaning the number of monitored interfaces that are up. The device with more healthy monitored ports wins, because it can forward traffic on more paths. The third is HA priority, which is a configurable integer from 0 to 255, where higher wins. The default is 128. The fourth is uptime, meaning the device that has been running longer wins, with a granularity that ignores small differences. The fifth and final tiebreaker is serial number, where alphabetically higher wins. The override setting deserves special attention. By default, override is disabled, which means once a device becomes primary it stays primary even if a higher priority device comes online. This is desirable behavior because it avoids unnecessary failovers. If you enable override, the cluster will actively move the primary role to the device with the highest priority whenever possible, which causes a failover every time your preferred primary reboots and comes back. Most production deployments leave override disabled. Session synchronization. The reason session synchronization matters is that a firewall is stateful. When a TCP connection is established through the firewall records the source and destination addresses, the source and destination ports, the sequence numbers, the NAT translation if any, and the security policy that allowed the session. Every subsequent packet in that connection is matched against the session table. If the session is not in the table, the packet is treated as a new connection, which for mid-connection packets means it gets dropped because there is no SYN. Without session synchronization, a failover would wipe every active connection. User browser sessions would reset, SSH sessions would disconnect, voice over IP calls would drop, and large file transfers would fail. With session synchronization, the secondary already has a copy of the session table, so when it becomes primary the existing connections continue without interruption. Let me walk through this sequence diagram showing how session sync works in practice. A client on the internal network initiates a TCP connection by sending a SYN to an external server. The primary FortiGate receives the SYN and applies its security policy, deciding to permit the connection. The primary creates a new session entry in its session table for this connection. The primary forwards the SYN out to the external server. Before the SYN acknowledge even comes back, the primary sends a session sync message to the secondary containing the new session entry. The secondary inserts the session into its own session table, and sends back an acknowledgement. The external server responds to the original client with a SYN acknowledge. The primary receives the SYN acknowledge, matches it against the existing session, and forwards it to the client. The client completes the three-way handshake with an acknowledge. Data flows between the client and server through the primary, and the primary continues to periodically sync the session state, including sequence numbers, to the secondary. Two important details. First, not all session types are synchronized by default. TCP sessions are synced when session pickup is enabled, but UDP and ICMP sessions are not synced by default because they are typically short-lived and the overhead of syncing them is not worth the benefit. You can enable UDP and PCONN sync separately if your workload needs it. Second, IPsec VPN sessions have their own separate synchronization mechanism, because re-establishing an IKE security association takes a round trip and a cryptographic exchange that you cannot simply replay from a session table entry. Session sync also has a cost. Under heavy connection rates, the sync traffic itself can saturate the heartbeat interface, which is why dedicated gigabit or 10 gigabit heartbeat links are important for high-throughput deployments. Fortigate exposes counters to monitor sync health, and I will show those in a later part of the series. On-premises HA physical topology. Let me now walk through what a typical on-premises Fortigate HA deployment looks like physically. This is the reference design that most mid-size and enterprise deployments follow. Let me describe this architecture diagram step by step. At the entry of our network we have the Internet, which represents the public Internet coming in from the ISP. The Internet connects to the ISP router, which is the demarcation point where the provider hands off connectivity to the customer. The ISP router connects to the external switch, which is a layer 2 switch on the outside of the firewall cluster. In high availability designs, this is typically a pair of switches or a switch stack, but for clarity we show it as a single logical switch. The external switch connects to both Fortigate A and Fortigate B on their way-in interfaces, labeled port 1 in our diagram. This means both FortiGates have physical connectivity to the outside world, but only the primary will actually forward traffic at any given time. Both FortiGates present the same cluster MAC address and cluster IP on this interface, which is how failover is transparent to the ISP router. On the inside of the cluster, Fortigate A and Fortigate B both connect to the internal switch on their LAN interfaces, labeled port 2. The internal switch connects down to the internal network, which represents the protected corporate network containing servers, clients, and other internal resources. Again, the cluster presents one shared MAC and IP on the inside, and the internal switch does not know or care which Fortigate is currently primary. Between the two FortiGates you can see two direct connections labeled HA1 and HA2. These are the heartbeat interfaces, and they are cabled directly between the two chassis without any switch in the path. HA1 is the primary heartbeat link and HA2 is the backup. Both links carry heartbeat packets, configuration sync, and session sync. Having two direct cables means the cluster survives a single cable cut or a single transceiver failure without entering split brain. The arrows on the diagram indicate where traffic flows. Real user traffic flows from the Internet through the ISP router, through the external switch, into Fortigate A, out of Fortigate A, through the internal switch, to the internal LAN. Fortigate B receives no user traffic in steady state and exists purely to take over if Fortigate A fails. The HA1 and HA2 links carry no user traffic, only FGCP. A few design considerations. The external and internal switches should themselves be redundant in a production deployment, typically using stacked switches or MLAG, because a switch failure on either side would partition the cluster from the network. The heartbeat cables should be physically separated, ideally routing through different cable trays, so that a single cable tray incident cannot sever both heartbeats simultaneously. Power should come from independent circuits, with each Fortigate on a different UPS and ideally a different PDU. On-premises HA-CLI configuration. Now let me walk through the actual Fortigate command line interface commands that configure an HA cluster. This is the exact sequence you would run on each device, typically on the device you want to be primary first, then on the future secondary. Both devices need matching HA parameters for the cluster to form. The first command, Config system HA enters the HA configuration context. Every HA-specific parameter is set within this context. This is a top-level system configuration section that applies globally to the device. Next, set mode A-P configures active-passive mode. The mode parameter accepts three values: A-P for active-passive, A-A for active-active, and standalone to effectively disable HA. We are choosing A-P because, as discussed earlier, it is the simpler and more common mode. If you wanted active-active for UTM scaling, you would set this to A-A instead. The set group name corp HA command assigns a human-readable name to the cluster. This is an identifier that appears in logs and on the GUI. It has no protocol meaning but makes operational troubleshooting easier. Any string up to 32 characters is valid. The setGroupID10 command assigns a numeric identifier to the cluster. This number, which accepts values from 0 to 255, is significant because it determines the cluster's virtual MAC addresses. Specifically, Fortigate derives the cluster MAC from the group ID. So if you have two separate Fortigate clusters on the same layer 2 segment, they must have different group IDs or their virtual MACs will collide. The default is 0, but I always recommend explicitly setting it per site. The set password FortiApp at SSW0RD command sets the FGCP authentication password. This password is included in heartbeat packets and is used to prevent a rogue Fortigate from accidentally or maliciously joining the cluster. Both cluster members must have the exact same password. Any printable string is accepted, and I strongly recommend a non-trivial value. The set HBDEV, HA1, 200, HA2, 100 command is the heart of the configuration. It designates which interfaces carry heartbeat traffic and assigns a priority to each. Higher priority is used first. So in this command, the interface named HA1 has priority 200 and is the primary heartbeat, and HA2 has priority 100 and is the backup. If you have dedicated HA ports on your hardware, they are typically named HA1 and HA2, but on smaller models you would substitute data interface names like port 9 and port 10. The priority values can be any integer from 0 to 512. The set session pickup enable command enables TCP session synchronization to the secondary. Without this, a failover would reset all active TCP connections. With it enabled, TCP sessions continue across a failover. This is almost always what you want, though it does add load to the heartbeat interfaces. Accepted values are enable or disable. The set session pickup connectionless enable command extends session sync to UDP and similar connectionless sessions. This is optional and depends on your workload. If you have heavy UDP applications like DNS or real-time media that would be disrupted by a failover, enable this. Otherwise, leaving it disabled reduces sync overhead. The set override disable command, which is the default, tells the cluster not to preempt a healthy primary when a higher priority device comes online. This means once a device is primary, it stays primary even if the other device reboots and comes back with higher priority. This prevents unnecessary failovers during maintenance. You would enable override only if you have a specific reason to force the primary role onto a preferred device. The set priority 200 command sets this specific device's election priority. Higher wins. The range is 0 to 255 and the default is 128. On the future secondary you would set this to a lower value, for example 100, so that if both devices come up simultaneously the intended primary wins the initial election. Once override is disabled and the cluster is running, priority only matters at cluster formation and at full cluster restart events. The set monitor, port 1, port 2, command designates which data interfaces the cluster monitors for failover triggering. If any monitored interface goes down on the primary, the cluster triggers a reevaluation and typically fails over to the secondary. You list the interfaces that carry real user traffic, which in our topology are port 1 facing the external switch and port 2 facing the internal switch. Do not list the heartbeat interfaces here, because a heartbeat failure is handled by the separate backup heartbeat mechanism. Finally, the end command commits the configuration and exits the context. After end, the device begins sending FGCP hellos on the designated heartbeat interfaces and will form a cluster as soon as a matching peer is reachable. That completes the on-premises design reference. We covered why HA matters, the two modes Fortigate supports, the FGCP protocol, cluster roles and election, heartbeat interfaces, session synchronization, failover behavior, on-premises topology, and the CLI configuration. Next we pivot to AWS, where the layer 2 assumptions that FGCP relies on do not hold, and we will see how Fortinet adapts HA for cloud environments using a PI-driven ROT and IP manipulation. Why on-premises HA does not work in AWS. Before we design Fortigate HA for AWS, we need to understand why the on-premises approach simply does not function in a public cloud. This is not a small adjustment, it is a fundamental architectural difference that forces a completely different failover mechanism. The on-premises FGCP design we covered earlier relies on 4 assumptions, and AWS violates every single one of them. The first assumption is Layer 2 broadcast. FGCP uses ether types beginning with 0x and ending with 90 and beginning with 0x and ending with 93 cent as Layer 2 multicast frames. AWS does not forward arbitrary Layer 2 frames between instances. The VPC is a software-defined Layer 3 network, and while it presents instances with a virtual Ethernet interface, the underlying transport is tunneled IP. Ether types that are not standard IPv4 or IPv6 simply get dropped. The second assumption is MAC address sharing. On-premises, a cluster of 2 FortiGates presents a single virtual MAC address on each interface, and both devices can claim that MAC. AWS enforces a strict one-to-one mapping between an elastic network interface, or ENI, and its MAC address. An ENI has exactly one MAC, and you cannot have 2 instances claiming the same MAC on the same subnet. The third assumption is gratuitous ARP. When failover happens on premises, the new primary sends gratuitous ARPs to make every upstream and downstream switch update its MAC table. AWS instances do not speak to physical switches. They speak to the AWS software-defined network, which maintains its own mapping of IP to ENI to hypervisor location. Gratuitous ARP packets have no effect on this mapping. The fourth assumption is promiscuous mode. On premises, both cluster members can see all traffic on the wire even if it is destined for the other device's MAC. AWS ENIs drop any frame not destined for their MAC, with no option to disable this behavior. Let me walk through this comparison diagram. It shows 2 parallel flows. The first flow represents on-prem FGCP and includes 3 checkboxes labeled Layer 2 Multicast Works, Shared Virtual MAC Works, and Gratuitous ARP Works, all connected to a final success node labeled FGCP Standard Mode, indicating that the traditional protocol functions as designed. The second flow represents AWS VPC and includes 3 crossed-out items labeled No Custom Ether Types, No MAC Sharing, and No Gratuitous ARP, all connected to a failure node labeled FGCP Standard Mode Broken, indicating that standard FGCP cannot work in this environment. The diagram makes the core point. AWS requires a different HA architecture, not just different configuration. The solution has 2 components that work together. Fortinet adapted FGCP itself to run over IP unicast instead of Layer 2 multicast, which handles the heartbeat and session sync communication between cluster members. And Fortinet added what they call the SDN connector, which lets the FortiGate make AWS API calls during failover to move IPs and ROTs around using AWS's own control plane. We will unpack both of these next. Unicast FGCP. Unicast FGCP is the adaptation of the Fortigate clustering protocol that allows it to run over a Layer 3 IP network like an AWS VPC. Functionally, it performs the same jobs as standard FGCP, including heartbeat, configuration synchronization, session synchronization, and election, but the transport is completely different. In standard FGCP, heartbeat packets are sent as layer 2 frames with ether type beginning with 0x88 and ending with 90, and session sync uses ether type beginning with 0x88 and ending with 93. Neither of these is IP. In unicast FGCP, both types of traffic are encapsulated in IP packets and sent as regular unicast between specific IP addresses that you configure on each cluster member. The Fortigate uses UDP for the heartbeat and a combination of UDP and TCP for sync, all destined for the peer's configured HA IP address. This shift has several important implications. First, the peer IP must be reachable via the VPC routing. Typically, both FortiGates sit in the same VPC but in different subnets, and the heartbeat traffic flows between their private IPs using a dedicated HA interface, often called Port 3 or Port 4, on a dedicated HA subnet. Second, because the traffic is regular IP, AWS security groups and network access control lists apply, and you must explicitly permit the FGCP heartbeat ports between the two FortiGate ENIs. Otherwise, the cluster never forms. Third, split brain risk is different because link-level failure detection by layer 2 does not exist. The cluster relies entirely on heartbeat timeouts, which tends to be slower to detect than a physical cable cut. Let me walk through this diagram showing the unicast FGCP flow. It depicts two FortiGate instances, FortiGate A primary and FortiGate B secondary, each with a dedicated HAENI. Between them you can see two labeled flows. The first flow is an arrow from FortiGate A to FortiGate B labeled UDP 703 heartbeat, which represents the periodic heartbeat packets sent from the primary to the secondary over unicast UDP on port 703. The second flow is a bidirectional arrow labeled TCP 703 session sync, representing the session synchronization traffic that uses TCP port 703 for reliable delivery of session state. Surrounding both FortiGates is a container labeled HA subnet, indicating that the HA interfaces live on the same dedicated subnet within the VPC, simplifying security group design and ensuring direct reachability. An additional container labeled VPC routing encloses the HA subnet and shows that the AWS VPC fabric is what actually carries these unicast packets between the two instances. A critical configuration detail. Each FortiGate needs to know its own HA IP address and its peer's HA IP address. Unlike on-premises where the cluster discovers peers through broadcast, unicast FGCP requires explicit peer configuration. We will see this in the CLI configuration slide at the end of this section. Single Availability Zone HA topology. The simplest AWS HA topology places both FortiGates in the same availability zone. This is the fastest failover topology because both devices share the same subnets and you can move private IPs between them directly without any routing changes. However, it does not protect against AZ failure, which is one of the main reasons you deploy in AWS in the first place. Let me walk through this diagram. You see a single container labeled Availability Zone A, which represents one physical data center cluster within an AWS region. Inside the AZ, you see 4 subnets. The public subnet contains a public ENI for FortiGate A primary and a public ENI for FortiGate B secondary, both connected to the same subnet. The private subnet similarly contains private ENIs for both FortiGates. The HA subnet contains the dedicated heartbeat ENIs for both, and the management subnet contains the management ENIs. The public subnet connects externally to an internet gateway, which is labeled IGW and represents the VPC's connection to the public internet. A public elastic IP is shown associated with the public ENI of FortiGate A, and an arrow labeled Cluster EIP indicates that this EIP will move to FortiGate B on failover. The private subnet has its own cluster private IP, which represents the secondary IP that holds the internal-facing cluster address. This IP is currently assigned to Fortigate HA's private ENI, and the arrow labeled private IP migrates on failover shows that the SDN connector will move it to Fortigate B when needed. Downstream of the private subnet you see a workload subnet representing application instances. A dashed arrow from workload subnet to Fortigate HA's private east NI is labeled default ROT via cluster IP, indicating that the workload ROT table sends outbound traffic to the cluster's floating private IP. When the cluster private IP migrates, the same ROT target still works because it points to an IP, not an ENI. The HA subnet shows a bidirectional arrow between the two FortiGates labeled Unicast FGCP, representing the heartbeat and session sync traffic flowing between them over AWS VPC networking. This topology is suitable for test environments, for workloads that do not require a Z-level resilience, or for cases where all downstream workloads are themselves in a single AZ. The failover is fast, often under 5 seconds, because no cross-AZ API calls are needed and ROT table updates are minimal. The trade-off is that an AWS AZ failure, while rare, takes down both FortiGates simultaneously. ROT table manipulation, the core mechanism. ROT table manipulation is the single most important concept to internalize for Cloud Fortigate HA. It is the mechanism by which traffic actually redirects from the old primary to the new primary after a failover. Without it, the Fortigate cluster can fail over perfectly and the network will still send traffic to a dead instance. Let me walk through this sequence diagram to show the ROT table update flow in detail. The participants are the workload instance, representing an application EC2 instance that needs to reach the internet through the firewall. The VPC ROT table, representing the AWS managed routing construct. The Fortigate A primary, which starts the scenario as the active device. The Fortigate B secondary, which starts as the passive device. And the AWS EC2 API, representing the AWS control plane that actually modifies ROT tables. The scenario begins in steady state. The workload instance sends an outbound packet destined for the internet. The VPC ROT table matches the default ROT and forwards the packet to the Fortigate A primary's ENI. Fortigate A processes the packet according to its security policy and forwards it onward. Now Fortigate A fails, perhaps due to an AWS instance termination, a kernel crash, or a monitored interface going down. Fortigate B detects the failure through missed heartbeats over the Unicast FGCP channel. Fortigate B promotes itself to primary. Fortigate B then invokes its SDN connector. The SDN connector on Fortigate-B makes an API call to the AWS EC2 API. The specific call is replace ROT, which takes a ROT table ID, a destination CIDR, and a new target ENI. The API request essentially says : for the ROT to quad 0/0 in ROT table beginning with a B and ending with 23. Change the target from ENI-primary to ENI-secondary. The AWS EC2 API processes this request and updates the VPC ROT table. The AWS control plane propagates the change to the data plane, which typically takes 1 to 3 seconds. Now the workload instance sends another outbound packet. The VPC route table matches the default ROT, which now has its target set to Fortigate-B's ENI, and forwards the packet to Fortigate-B. Fortigate-B processes the packet using its copy of the session table, which was synced from Fortigate-A before the failure, and forwards it onward. From the workload instance's perspective, a brief packet loss window occurred but the session continues. The API call completes and Fortigate-B acknowledges the successful ROT update. The cluster is now fully operational with Fortigate-B as the active primary. Two practical details matter here. First, a single VPC can have many ROT tables, one per subnet or shared across subnets, and the SDN connector must update every ROT table that should send traffic to the Fortigate. The administrator configures these route table IDs explicitly in the SDN connector configuration. Second, route propagation latency is real. The API call returns success quickly, but the data plane takes a moment to catch up, which is part of the reason cloud failover is slower than on-premises. IAM permissions for the SDN connector. The SDN connector must authenticate to AWS before it can make API calls. AWS supports two authentication models for this: an IAM role attached to the Fortigate EC2 instance, or static access keys configured on the Fortigate. The best practice, always, is to use an IAM role. Static access keys are rotated less frequently, leak more easily, and create operational friction. An IAM role attached to the Fortigate instance means that when the SDN connector makes an API call, it automatically picks up temporary credentials from the EC2 instance metadata service, uses them to sign the API request, and never needs the administrator to manage or rotate a secret. The role must be attached at instance launch time or later via instance modification, and the role's trust policy must allow the EC2 service to assume it. The permissions attached to the role should follow the principle of least privilege. The SDN connector needs a specific set of EC2 actions, and granting broader permissions creates unnecessary security risk. Let me walk through the JSON policy on this slide. The policy document opens with the version field set to 2012-10-17, which is the current IAM policy language version and should always be this value. The statement array then contains a single object describing the allowed actions. The effect field is set to allow, meaning the listed actions are permitted. The alternative would be deny, but for a role that is purely granting permissions, allow is what you want. The action array lists the specific EC2 API actions the SDN connector needs. The first action, EC2 describe instances, lets the connector query information about EC2 instances, which it uses to discover its peers' ENIs. The action EC2 describe network interfaces lets it query ENI details, which is needed to find the ENIs it will modify. The action EC2 describe route tables lets it enumerate the route tables in the VPC, so it can find the ones it needs to update. The action EC2 replace route as the core failover action, letting the connector modify route targets in VPC route tables. The action EC2 associate address reattaches an elastic IP to a new ENI during failover. The action EC2 disassociate address removes an elastic IP from its current ENI, which is the first half of an EIP migration. The action EC2 assign private IPs attaches a secondary private IP to an ENI on the new primary. The action EC2 unassigned private IPs removes a secondary private IP from the old primary's ENI. Finally, EC2 describe addresses lets the connector query elastic IP details to find the ones it manages. The resource field is set to the wildcard, an asterisk, which means the actions apply to any resource in the account. For most deployments this is acceptable because the Fortigate role is already scoped to a specific VPC's resources through the actions themselves. If you need tighter scoping, you can restrict the resource field to specific ARNs, but this requires careful matching of the resource types each action expects, and it is easy to accidentally block legitimate operations. Once this policy is attached to the Fortigate's IAM role, and the role is attached to the instance, the SDN connector can function without any credentials configured on the Fortigate itself. The use metadata IAM setting in the Fortigate SDN connector configuration tells it to pull credentials from the instance metadata service automatically. AWS HA command line interface configuration. Let me walk through the Fortigate CLI configuration that stitches all of this together. This sequence runs on each Fortigate in the cluster, with the HA-specific values differing per device and the SDN connector values being identical. The first block is the HA configuration. The configure system HA command enters the HA context, same as on premises. The set mode AP configures active-passive mode, which is the only supported mode for AWS GCP deployments because active-active's load balancing logic depends on layer 2 behavior that does not exist in AWS. The set group name AWS FGTHA gives the cluster a human-readable identifier for logs and GUI display. The set group ID 1 sets the numeric group ID. In AWS, this has less importance than on-premises because there is no virtual MAC derivation, but it still must match between peers and helps distinguish clusters if you have multiple in the same VPC. The set HB dev port 3100 designates port 3 as the heartbeat interface with priority 100. In AWS deployments, port 3 is typically the ENI attached to the dedicated HA subnet. Only one heartbeat interface is listed because AWS does not have the physical cabling model of on-premises. You would simulate redundancy through VPC path diversity, not multiple heartbeat ENIs. The set session pickup enable turns on TCP session synchronization, same as on-premises, so that failover does not tear down existing TCP connections. The set HA management status enable allows the management interface to remain reachable independently of the cluster state, meaning you can administer the secondary directly even when it is not primary. This is essential in AWS where you may need to SSH into the secondary for troubleshooting. The configuration HA management interfaces sub-block defines which interface provides independent management access. Inside the sub-block, Edit 1 creates or edits entry 1. Set interface port 4 designates port 4 as the management interface, and set gateway 10.0.3.1 sets the default gateway used for management sourced traffic. The end terminates the sub-block, then next terminates the entry. The set unicast heartbeat enable is the critical AWS specific setting. This switches FGCP heartbeat from multicast layer 2 to unicast layer 3. Without this, the cluster will never form in AWS. The set unicast-HB-peer IP 10.0.2.11 sets the peer's HA interface IP address. On Fortigate-A this is Fortigate-B's HA IP, and on Fortigate-B this is Fortigate-A's HA IP. This is the explicit peer discovery that replaces the broadcast discovery used on premises. The set unicast HB netmask 255.255.255.0 sets the netmask for the HA interface subnet, so the FortiGate knows the scope of the HA network. The set priority 200 sets the election priority for this specific device. On the future secondary you would set a lower value, typically 100. So that the intended primary wins the initial election. The end commits the HA configuration block. The second block configures the SDN connector. The config system SDN connector enters the connector context. The edit AWS HA creates a new connector named AWS HA, which is a label you choose. The set type AWS declares this as an AWS SDN connector. Fortigate supports many connector types including Azure, Google CP, Kubernetes, and OCI, but for our AWS deployment we choose AWS. The set use metadata IAM enabled tells the connector to retrieve credentials from the EC2 instance metadata service rather than using configured access keys. This requires the IAM role we discussed in the previous slide to be attached to the instance. It is the secure and recommended approach. The set update interval 60 sets how often the connector refreshes dynamic address and object information from AWS. This value is in seconds, and accepts integers from 30 to 3600. 60 seconds is a reasonable default that balances freshness against a PI call volume. This only applies to dynamic object refresh. Failover triggers a PI calls immediately regardless of this interval. The next terminates the connector entry and end commits the configuration. After this configuration, both FortiGate's running matching configurations will form a cluster, elect a primary, and the primary's SDN connector will be ready to call AWS APIs during any future failover event. At this point you would also configure your VPC route tables to point to the primary's private ENI, associate any elastic IPs with the primary's public ENI, and configure security groups to permit unicast FGCP traffic between the two HA ENIs on TCP and UDP port 703. That completes the AWS HA reference architecture. The key mental model to carry forward. On-premises HA moves MACs and sends gratuitous ARPs. AWS HA moves IPs and rewrites route tables via PI calls. Next we will apply the same concepts to Azure, where the mechanisms are similar but the specific cloud primitives differ. Fortigate HA in Azure. We now move from AWS to Microsoft Azure. Azure shares the fundamental public cloud constraint that forced AWS to abandon Layer 2 FGCP. The Azure Virtual Network is a software-defined Layer 3 fabric. It does not forward arbitrary ether types between virtual machines, and network interfaces are bound to specific MACs that cannot be shared. So everything we learned about unicast FGCP applies here as well. The heartbeat still runs over IP. The SDN connector still calls cloud APIs to redirect traffic, and the high-level mental model stays the same. What changes is almost every specific detail. Azure uses different primitives to achieve the same outcomes. Where AWS has elastic IPs, Azure has public IP addresses with different allocation semantics. Where AWS has VPC route tables, Azure has route tables attached to subnets as user-defined routes, or UDRs. Where AWS has ENIs with multiple private IPs, Azure has network interfaces with IP configurations. And where AWS offers exactly one primary HA pattern for FGCP, Azure offers two fundamentally different patterns that you must choose between at design time. The two Azure HA patterns are active-passive with the SDN connector, conceptually equivalent to the AWS design we just covered, and active-active with Azure load balancers in what is called a sandwich design, which is unique to Azure and has no direct AWS equivalent in the FGCP world. The sandwich design uses standard load balancers in front of and behind the FortiGate pair to distribute traffic at the IP level without requiring the FortiGates to coordinate IP ownership at all. In this section we will cover both patterns. We will start with the SDN connector approach because it maps directly to what you just learned about AWS. Then we will cover the load balancer sandwich because it is a common production pattern in Azure and solves problems that the SDN connector approach does not. We will also cover the Azure-specific constraints like availability sets versus availability zones, the way Azure Accelerated Networking interacts with HA, and the managed identity model that replaces AWS IAM roles. Azure SDN Connector HA Architecture. Let me walk through the SDN Connector HA architecture in Azure. Conceptually, this is the Azure equivalent of the AWS FGCP unicast design, but it uses Azure primitives throughout. Let me walk through this diagram. The outer container represents an Azure Virtual Network, labeled VNet, which is Azure's term for what AWS calls a VP circuit. Inside the VNet you see 4 subnets. The external subnet hosts the external-facing network interfaces of both FortiGates. The internal subnet hosts the internal-facing interfaces. The HA Sync subnet hosts dedicated heartbeat interfaces. The management subnet hosts management interfaces. 2 FortiGates are deployed in the VNet, FortiGate A primary and FortiGate B secondary. Each FortiGate has a network interface, or NIC, in each of the 4 subnets. NICs in Azure are distinct resources from the virtual machines that use them, which is an important architectural detail. The NIC's IP addresses persist independently of the VM. The external subnet is where external traffic arrives. You see a public IP address resource associated with Fortigate HA's external NIC. This public IP is the cluster's internet-facing address and will move to Fortigate B's external NIC during failover via the SDN connector. The arrow from the Internet to the public IP represents inbound traffic from the Internet. Outbound workload traffic uses a different mechanism. You see a workload subnet separately in the VNet, containing workload virtual machines. A route table resource is attached to the workload subnet, labeled UDR with default ROT quad 0/0. The UDR's next hop target is Fortigate HA's internal NIC IP address, shown by an arrow from the UDR to Fortigate HA's internal NIC labeled next hop IP. Between Fortigate A and Fortigate B, you see a bidirectional arrow labeled Unicast FGCP, representing heartbeat and session sync traffic flowing over the HA sync subnet. This works identically to the AWS design. FGCP packets are encapsulated in IP and sent as unicast between the two configured peer IPs. The SDN connector is depicted as a component inside Fortigate A's primary instance, with an arrow labeled HTTPS API calls reaching out to the Azure Resource Manager API endpoint. Azure Resource Manager, or ARM, is the control plane for all Azure resources. The SDN connector authenticates to ARM using a managed identity, and it issues API calls to update three things during failover: the public IP association, the internal NIC's secondary IP configurations, and the UDR next hop targets. A dotted line from the FortiGate primary to an Azure AD managed identity resource shows the authentication path. We will cover managed identities specifically in a later slide, but the short version is that Azure assigns an identity to the FortiGate virtual machine itself, and that identity is granted permissions on the resources it needs to modify. Azure Public IP and Private IP migration. Azure public IPs and private IP configurations behave differently from their AWS equivalents, and these differences affect HA design. Let me walk through both. Azure public IP addresses are Azure resources in their own right, with their own lifecycle. They come in two SKUs, basic and standard, and two allocation types, dynamic and static. For high availability, you always use a standard SKU with static allocation. The basic SKU has significant limitations including no zone redundancy and deprecated features. Static allocation means the IP address is reserved and does not change even if the public IP is disassociated and reassociated. A public IP is associated with an IP configuration on a NIC. When the SDN connector migrates a public IP, it disassociates it from the old primary's NIC and reassociates it with the new primary's NIC. This is a two-step API operation that takes a few seconds each step. Unlike AWS, where the elastic IP can move atomically, Azure requires the explicit disassociate then associate sequence. For private IPs, Azure NICs support multiple IP configurations. Each IP configuration has a primary private IP that is fixed, and optionally additional secondary IPs. Just like AWS, the primary IP cannot move between NICs, but secondary IPs can. For single-zone HA designs, a secondary private IP can be moved between the two Fortigate NICs to act as the cluster's floating internal address. However, this only works within the same subnet, and Azure's behavior around this has some sharp edges worth knowing. Let me walk through this diagram showing the before and after states. The left side shows steady state with Fortigate A as primary. Fortigate A's external NIC has a primary private IP, a secondary private IP serving as the cluster internal facing IP, and an associated public IP resource. Fortigate B's external NIC has only its primary private IP. The right side shows post-failover state. Fortigate A retains only its primary private IP. The secondary private IP and the public IP association have both moved to Fortigate B's external NIC. Fortigate B is now the primary. Between the two states you see arrows representing the Azure API calls invoked by the SDN connector. The arrows are labeled with the Azure-specific operations. Remove IP configuration and disassociate public IP from Fortigate A's NIC. and add IP configuration and associate public IP to Fortigate B's NIC. These are put operations against the network interface resources in Azure Resource Manager. An important Azure-specific detail. Azure NIC's cache IP configurations for DHCP assignment to the virtual machine. When you add or remove IP configurations via a PI, the virtual machine's operating system does not automatically pick up the change unless the NIC is refreshed. Fortigate handles this internally by forcing a NIC refresh as part of the SDN connector operation. But if you are troubleshooting a failed migration, the NIC state in the Azure portal is what you should trust. Availability zones and availability sets. Azure has two redundancy constructs for placing virtual machines: availability sets and availability zones. Both affect how you design Fortigate HA, and the choice has real implications for SLA and failover behavior. An availability set is the older construct. It places virtual machines across multiple fault domains and update domains within a single Azure data center. A fault domain is a shared set of hardware, power, and network infrastructure, and Azure guarantees that virtual machines in different fault domains do not share these. An update domain is a group of virtual machines that Azure will reboot together during platform maintenance. Availability sets protect against hardware failure and planned maintenance but not against a full data center failure. An availability zone is the newer construct and is equivalent to an AWS availability zone. Each zone is a physically separate data center within an Azure region, with independent power, cooling, and networking. Zone redundant deployments protect against a full data center failure. Not all Azure regions support availability zones, so you must verify availability before designing zone-based HA. Let me walk through this comparison diagram. It shows three deployment topologies side by side. The first topology is labeled Single Data Center with Availability Set and shows a data center container holding Fortigate A and Fortigate B, both in the same availability set construct with different fault domains indicated. The second topology is labeled Availability Zone Deployment and shows two separate data center containers, Zone 1 and Zone 2, each holding one Fortigate. The third topology is labeled Mixed, which is not supported, showing a Fortigate in an availability set and a Fortigate in an availability zone, with an X through the arrangement indicating incompatibility. You cannot mix zone and set membership for members of the same Fortigate HA cluster. For Fortigate HA, I recommend availability zones wherever the region supports them. The zone failure protection is substantially better than availability sets, and the added latency between zones is typically under 2 milliseconds, well within GCP tolerances. The main reason to use availability sets is when deploying to a region that does not support zones, or when cost is a primary driver and single zone HA is acceptable. For load balancer sandwich HA, both the public SLB and internal SLB must be standard SKU to support availability zones. The load balancers themselves can be zone redundant, and the backend Fortigates can be spread across zones, giving you full zone failure tolerance at both the load balancing and firewall tiers. One important constraint: an Azure VNet spans all zones in a region, and subnets are regional resources not tied to a specific zone. Unlike AWS where subnets are AZ-bound, Azure subnets can contain virtual machines from any zone within the region. This simplifies some aspects of HA design because you do not need separate subnets per zone for the Fortigate interfaces. Azure HA failover sequence. Let me walk through the complete Azure failover sequence to tie all the concepts together. This is the end-to-end view of what happens when the primary Fortigate fails in an SDN connector HA deployment. Let me walk through this sequence diagram. The participants are the workload virtual machine representing an application instance, the Azure UDR representing the route table controlling workload egress, Fortigate A as the initial primary, Fortigate B as the initial secondary, and Azure Resource Manager as the cloud control plane. In steady state, the workload virtual machine sends outbound traffic. The Azure UDR matches the default route and forwards the packet to Fortigate A. Fortigate A applies policy and forwards the traffic to its destination. Fortigate A continuously sends FGCP heartbeats over the HA sync subnet to Fortigate B, which acknowledges them. Fortigate A also syncs session state to Fortigate B periodically so that the secondary has current knowledge of active connections. A failure event occurs on Fortigate A. This could be an instance crash, a guest OS hang, or an Azure platform event that makes the virtual machine unreachable. Fortigate B stops receiving heartbeat packets. After the configured heartbeat threshold is exceeded, Fortigate B declares Fortigate A failed. Fortigate B promotes itself to primary. Fortigate-B's SDN connector wakes up and begins its failover API sequence. The first call is to Azure Resource Manager requesting an update to the UDR's next hop IP, changing it from Fortigate-A's internal IP to Fortigate-B's internal IP. Azure Resource Manager accepts the request and begins propagating the change to the VNet data plane. This takes several seconds. The SDN connector makes a second call to Azure Resource Manager to update the external NIC, disassociating the public IP from Fortigate-A's NIC. Azure Resource Manager processes the disassociation. The SDN connector makes a third call to associate the public IP with Fortigate-B's external NIC. Azure Resource Manager processes the association and propagates the change to the public IP forwarding infrastructure. If secondary private IPs need to move, the SDN connector makes additional calls to remove the IP configuration from Fortigate-A's NIC and add it to Fortigate-B's NIC. Each of these is a separate ARM put operation and takes a few seconds each. Once ARM propagation completes, the workload virtual machine sends its next outbound packet. The UDR now points to Fortigate-B. The packet is forwarded to Fortigate-B, which uses its synced session table to recognize the connection, applies policy, and forwards to the destination. From the workload virtual machine's perspective, a brief packet loss window occurred but the session continued through the failover. The entire sequence typically takes 10 to 30 seconds, with the variation coming from how many API calls must be made and how quickly Azure Resource Manager propagates each change. This is significantly slower than on-premises FGCP failover but comparable to other cloud firewall HA implementations. Azure HA CLI configuration. Let me walk through the Fortigate command line interface configuration for Azure HA using the SDN connector pattern. This combines the HA cluster configuration with the Azure-specific SDN connector block. The first block is the HA configuration. The config system HA command enters the HA context. The set mode AP configures active-passive mode, which is the mode used for SDN connector HA in Azure. The set group name Azure FGTHA provides the cluster name for logs and management. The set group ID 1 sets the numeric cluster ID. This must match between peers. The set HB dev port 3100 designates port 3 as the heartbeat interface with priority 100. In Azure deployments, this corresponds to the NIC attached to the HA sync subnet. The set session pickup enable turns on TCP session synchronization so that failover preserves existing connections. The set session pickup connectionless enable extends synchronization to UDP and ICMP sessions, which matters if your workload is UDP heavy like DNS or real-time media. The set HA-management-status enable allows independent management access to each Fortigate, essential for troubleshooting the secondary when it is not primary. The config HA management interfaces block designates the management interface. The edit 1 creates entry 1. The set interface port 4 assigns port 4 as the management interface, which typically sits in the management subnet. The set gateway 10.0.4.1 sets the default gateway for management sourced traffic. The end closes the sub-block. The set unicast-HB enable activates unicast FGCP, required for Azure just as it is required for AWS. The set unicast-hb-peer IP 10.0.3.11 sets the peer's HA network interface controller IP address. On Fortigate-A, this is Fortigate-B's HA IP, and on Fortigate-B this value is reversed. The set priority 200 sets this specific device's election priority. On the future secondary, you would configure this as 100 instead, so the intended primary wins the initial election. The end commits the HA configuration. The second block configures the Azure SDN connector. The config system SDN connector command enters the connector context. The edit Azure-HA creates a connector named Azure-HA. The set type Azure declares this as an Azure connector, as opposed to AWS, GCP, or other supported types. The set use metadata IAM enable tells the connector to retrieve credentials from the Azure Instance Metadata Service using the managed identity we discussed. This replaces the need to configure a client ID and client secret on the Fortigate. The set HA-status enable explicitly activates the HA-specific behavior of the connector, telling it to manage resources on failover events. The set resource group Fortigate HA specifies the Azure resource group containing the Fortigate cluster resources. Resource groups are Azure's logical container for related resources, and the SDN connector needs to know which one to target. The set subscription ID ABCD 1234-EF56-7890-ABCD-EF 1,234,567,890 sets the Azure subscription ID. This is a GUID that uniquely identifies your Azure subscription. The connector needs this to construct valid ARM resource URIs. The set update interval 60 sets the dynamic object refresh interval in seconds. The connector will refresh address objects and other dynamic resources at this frequency. Failover API calls are still immediate and not affected by this interval. The next ends the connector entry and end commits the configuration. Finally, we define the specific routes that the connector should manage. The config NIC section would declare the NICs the connector monitors, and a config route section would declare the UDRs. In practice, the SDN connector auto discovers these based on tags or explicit configuration, and the exact syntax varies by Fortios version. The key operational requirement. Every UDR next hop that should point to the current primary must be enumerated in the SDN connector configuration, otherwise the connector will not update it during failover. After this configuration is in place on both FortiGates, and the managed identities have the appropriate role-based access control role assignments, the cluster will form and the SDN connector will be ready to handle failover events. That completes the Azure HA reference architecture. The mental model to carry forward is identical to AWS at the conceptual level. Unicast FGCP between the peers. SDN connector calling cloud APIs to redirect traffic. Only the specific primitives change. Next we apply the same patterns to Google Cloud. Fortigate HA in Google Cloud. We now move to Google Cloud Platform, or GCP. Like AWS and Azure, GCP enforces a Layer 3 software-defined network that does not forward arbitrary ether types, does not allow MAC sharing across instances, and does not propagate gratuitous ARP. So the core principle carries over. Standard FGCP cannot run natively, and Fortigate uses Unicast FGCP for heartbeat and session sync, plus the SDN connector for cloud API manipulation during failover. What makes Google CP different from AWS and Azure comes down to three architectural distinctions that change how HA is designed. The first is that Google CP VPC networks are global, not regional. A single VPC can span every Google CP region simultaneously, and subnets are regional resources that span all zones within a region. This is genuinely different from AWS where VPCs are regional and subnets are zonal, and from Azure where VNets are regional and subnets are regional but tied to a VNet. The practical effect is that you can place your two FortiGates in different zones of the same region and have them share a subnet. The second distinction is that Google CP routes are top-level VPC resources, not subnet-attached route tables. A route in Google CP applies to the entire VPC network globally and is selected for a given packet based on destination match and route priority. This means there is no concept of a per-subnet route table. Instead, all routes for the VPC live in one global routing space with priority-based selection. This fundamentally changes how failover manipulates routing. The third distinction is that GCP uses service accounts rather than AWS IAM roles or Azure managed identities. A service account is a special kind of identity that Google Cloud Virtual Machines can act as, and it is granted permissions through IAM role bindings on specific resources. For high availability patterns, Google CP supports two main approaches that mirror what we saw in Azure. The first is route-based high availability with the SDN connector, where priority-based VPC route manipulation redirects traffic on failover. The second is internal TCP/UDP load balancer as next hop, where a Google CP internal load balancer sits in front of two active FortiGates and distributes traffic, conceptually similar to the Azure load balancer sandwich. In this section we cover both. Google CP SDN Connector HA architecture. Let me walk through the GCP SDN Connector HA architecture. The structure resembles the AWS and Azure designs, but the GCP primitives introduce some meaningful differences worth internalizing. Let me walk through this diagram. The outer container represents a GCP project, which is the fundamental resource container in GCP and the billing boundary. Inside the project you see a VPC network, which is a global resource spanning all GCP regions. Inside the VPC network you see a single GCP region, labeled US Central 1 in our example, representing one Google data center cluster. Within the region you see two zones, Zone A and Zone B, each representing a physically distinct data center within that region. The VPC network contains 4 subnets. The external subnet carries external-facing interfaces. The internal subnet carries internal-facing interfaces. The HA sync subnet carries heartbeat interfaces. The management subnet carries management interfaces. Critically, each of these subnets is a regional resource, meaning it exists across both Zone A and Zone B simultaneously. This is different from AWS where subnets are zone-bound. Fortigate HA primary is deployed in Zone A. Its external NIC, internal NIC, HA NIC, and management NIC all live in the corresponding subnets. Fortigate B secondary is deployed in Zone B. Its 4 NICs live in the same subnets as Fortigate A's, because subnets are regional. This is a clean simplification compared to AWS where you need subnet replication per zone. External traffic enters via a Google CP external IP resource, shown in the diagram as a reserved IP that is currently associated with Fortigate A's external NIC. The arrow from the internet reaches this external IP, and from the external IP to Fortigate A's external NIC. The external IP will migrate to Fortigate B's external NIC during failover via the SDN connector. Outbound workload traffic flows through VPC routes. The diagram shows a workload subnet containing workload virtual machines. Workload virtual machines send outbound traffic, which the VPC network evaluates against its global route table. 2 routes are shown. A primary route with destination quad 0/0 and next hop Fortigate-A's internal NIC, priority 100, and a backup route with the same destination but next hop Fortigate-B's internal NIC, priority 200. The lower priority number wins, so the primary route is selected. The arrow from the VPC network to Fortigate-A's internal NIC represents the selected route's forwarding behavior. Between Fortigate A's HANIC and Fortigate B's HANIC, you see a bidirectional arrow labeled Unicast FGCP, representing heartbeat and session sync traffic flowing over GCP's VPC fabric between zones. GCP guarantees low interzone latency, typically under 2 milliseconds within a region. The SDN connector component inside Fortigate A's primary instance is shown with an arrow labeled HTTPS, API calls reaching out to the Google Compute Engine, a PI endpoint, representing the control plane. A dotted line from Fortigate A to a service account resource represents the authentication binding, which we will cover in detail later. The service account identity is used by the SDN connector to authenticate its API calls to Google Cloud. Internal load balancer as next hop. The ILB as next hop pattern is a Google CP native HA approach that does not rely on the SDN connector or on priority-based route manipulation. It uses a Google CP internal TCP UDP load balancer configured with 2 active FortiGates as backends, and VPC routes point to the load balancer's front-end IP as their next hop. Let me walk through this diagram. The outer container is the VPC network. Inside you see a region containing 2 zones, Zone A and Zone B. Fortigate A is deployed in Zone A, and Fortigate B is deployed in Zone B, both active simultaneously with no primary-secondary distinction. Both FortiGates are members of an instance group, shown in the diagram as a resource containing both instances. Google Cloud Platform instance groups are a logical grouping of compute instances used as backends for load balancers. For high availability across zones, a specific type called an unmanaged instance group per zone is used, with both instance groups attached to the same backend service. The diagram shows an unmanaged instance group A containing Fortigate A and unmanaged instance group B containing Fortigate B. A GCP internal TCP UDP load balancer is depicted with 2 components. The backend service connects to both instance groups, meaning traffic can be sent to any Fortigate in either group. The forwarding rule holds the internal front-end IP address, which is the target that VPC routes will point to. An arrow labeled HealthCheck connects the backend service to both FortiGates, representing the periodic probes the load balancer sends to each Fortigate to determine its health. For routing, you see a workload subnet with workload virtual machines. A VPC route is shown with destination quad 0/0 and next hop set to the internal front-end IP of the ILB. When a workload virtual machine sends outbound traffic, the VPC evaluates its routes, selects this route, and forwards the packet to the ILB's front-end IP. The ILB distributes the flow to one of the 2 FortiGates based on its session affinity setting, typically a 5-tuple or 3-tuple hash. A special GCP feature enables this pattern. The ILB must be configured with the next hop ILB flag at route creation time, which allows a route to target a load balancer's front-end IP as a next hop. Without this configuration, GCP would reject the route because normally you cannot point a route at a load balancer. For inbound traffic, a similar pattern applies but using an external load balancer or a second internal load balancer sitting on the external side. The details vary by traffic pattern, but the core idea is the same. The ILB handles distribution and health checking, and the FortiGates are stateless participants from the perspective of HA coordination. The failover mechanism is entirely different from the SDN connector pattern. The ILB health check probes each Fortigate, typically on a dedicated TCP port like 8008 configured on the Fortigate as a health check listener, at a configurable interval. If probes fail for the configured threshold, the ILB marks the backend unhealthy and stops distributing new flows to it. Existing flows on the surviving Fortigate are unaffected, and new flows are hashed only to the healthy backend. Failover detection is typically 5 to 15 seconds depending on probe configuration. A critical consideration. This pattern does not synchronize sessions by default. When a Fortigate fails, Any flows it was handling are dropped and the clients must reconnect, at which point the ILB hashes the new flow to the surviving Fortigate. If you need session persistence through failover, you enable Fortigate Session Synchronization, or FGSP, between the two Fortigates, similar to the Azure LB sandwich pattern. This adds sync overhead but gives you stateful failover under the ILB architecture. Regions, zones, and subnet behavior. Google CP's region and zone model has important implications for Fortigate HA design, particularly the fact that subnets are regional rather than zonal. Let me walk through what this means in practice. A GCP region is a geographic area containing multiple isolated data center locations called zones. Regions are identified by names like US Central 1 or Europe West 3. Each region has typically 3 or 4 zones, identified by appending a letter like US Central 1-A or US Central 1-B. Zones within a region are connected by low latency, high bandwidth private links, typically with sub-millisecond latency between zones. The key distinction from AWS and Azure is the subnet behavior. In AWS, a subnet belongs to exactly one availability zone, and a VPC that spans multiple AZs needs separate subnets in each. In Azure, a subnet is a VNet-level resource that can hold virtual machines from any zone but is not zone-scoped itself, which is already more flexible than AWS. In GCP, a subnet is a regional resource that automatically exists across all zones in that region. A single subnet in US Central 1 is simultaneously present in US Central 1A, US Central 1B, US Central 1C, and US Central 1F, and you can place virtual machines from any of those zones into the same subnet. Let me walk through this topology diagram. The outer container is a single GCP VPC network, which is a global resource. Inside you see the region US Central 1. Inside the region are 4 zones: US Central 1-A, US Central 1-B, US Central 1-C, and US Central 1-F. A subnet labeled external subnet with CIDR 10.0.1.0/24 is shown spanning all 4 zones as a single regional resource. The arrows from the subnet extend into each zone showing its presence. Fortigate A is placed in zone US Central 1-A with its external NIC in the external subnet. Fortigate B is placed in zone US Central 1-B with its external NIC also in the external subnet. Because the subnet is regional, both Fortigates share the same subnet despite being in different zones. This means they can also share the same alias IP range by moving it between their NICs, something not directly possible cross-zone in AWS. The practical benefits of this model for HA are significant. You do not need to create mirror image subnets per zone. You can move alias IP ranges between zones within the same subnet via PI. VPC routes point to instance names in specific zones rather than to subnet-scoped ENIs. And VPC firewall rules, which are Google CP's equivalent to security groups, apply at the VPC or network tag level rather than per subnet, further simplifying configuration. For high availability designs that need regional resilience, you place the two Fortigates in different zones of the same region. For designs that need multi-region resilience, you deploy separate Fortigate clusters in each region and use mechanisms like Cloud DNS, global load balancers, or client-side routing to distribute traffic across regions. A single Fortigate high availability cluster does not span regions because FGCP heartbeat tolerances are tight enough that inter-region latency would cause instability. One more consideration. Google CP's global VPC means that resources in different regions can communicate privately without traversing the internet, using the same VPC's internal routing. This enables designs where a central hub VPC contains firewall clusters and multiple regions share that security enforcement, though this introduces its own design considerations beyond the scope of basic HA. Google CP HA failover sequence. Let me walk through the complete Google CP failover sequence for the ROT-based HA pattern with SDN connector. This ties together everything we have covered about ROTs, external IPs, alias IPs, and the service account authentication model. Let me walk through this sequence diagram. The participants are the workload virtual machine representing an application instance, the VPC network representing the global Google CP routing fabric, Fortigate A as the initial primary, Fortigate B as the initial secondary, and the Google Compute Engine API as the cloud control plane. In steady state, the workload virtual machine sends outbound traffic. The VPC network evaluates all ROTs matching the destination, selects the ROT with the lowest priority value, which is the ROT with priority 100 pointing to Fortigate A. The packet is forwarded to Fortigate A's internal NIC. Fortigate A applies security policy and forwards the traffic to its destination. Fortigate A continuously sends unicast FGCP heartbeats to Fortigate B over the HA sync subnet, and Fortigate B acknowledges each heartbeat. Fortigate A also syncs session state periodically so Fortigate B has current connection knowledge. Fortigate A fails. This could be a guest OS crash, a GCE platform event, or a preemption if using preemptible instances. Though preemptible instances should never be used for production HA. Fortigate B stops receiving heartbeats. After the configured heartbeat threshold elapses, Fortigate B declares Fortigate A failed. Fortigate B promotes itself to primary. Fortigate B's SDN connector wakes up and begins the failover API sequence. The first API call is to the Google Compute Engine API, specifically a delete request against the primary ROT named FGT default primary. This removes the ROT pointing to Fortigate A. At this moment the backup ROT with priority 200 pointing to Fortigate B becomes the only matching ROT, and the VPC fabric begins selecting it for traffic. The SDN connector then makes a post request to create a new primary ROT pointing to Fortigate B with priority 100. This restores the normal 2 ROT configuration with the old backup still at priority 200 and the new primary at priority 100 targeting Fortigate B. The VPC fabric propagates the ROT change across all zones, typically in 5 to 10 seconds. If external IP migration is needed, the SDN connector makes a patch request to remove the access configuration containing the external IP from Fortigate A's network interface. Then another patch request to add an access configuration with the same external IP to Fortigate B's network interface. These are sequential operations and each takes a few seconds. If alias IP ranges need to migrate, the SDN connector makes additional patch requests to remove the alias IP range from Fortigate A's NIC and add it to Fortigate B's NIC. Each is a separate API call. Once all API calls complete and Google CP propagates the changes, the workload virtual machine sends its next packet. The VPC network evaluates ROTs, finds the new primary ROT pointing to Fortigate B, and forwards the packet. Fortigate B uses its synced session table to recognize the connection, applies policy, and forwards to the destination. The session continues uninterrupted from the application perspective, with only a brief packet loss window. Typical total failover time for Google CP ROT-based HA is 10 to 25 seconds, comparable to AWS and Azure. The time is dominated by ROT propagation across the VPC fabric and API call sequencing, not by FGCP heartbeat detection, which is sub-second. Google CP HA CLI configuration. Let me walk through the complete Fortigate command line interface configuration for Google Cloud Platform HA using the ROT-based pattern with SDN connector. Each parameter in this configuration has a specific purpose, and we will cover every line. The first block is the HA configuration. The config system HA command enters the HA configuration context, which is where all cluster parameters live. The set mode A-P line configures active-passive mode. This is the mode used for ROT-based HA in GCP. Active mode is not supported for Cloud FGCP deployments because its load balancing logic depends on Layer 2 behavior. The set group name GCP FGTHA line sets a human-readable cluster identifier that appears in logs and on the GUI. The set group ID 1 line sets the numeric cluster ID. This value must match between the two peers for the cluster to form. The set HB dev port 3100 line designates port 3 as the heartbeat interface with priority 100. In GCP, this corresponds to the NIC placed in the HA sync subnet. The set session pickup enable line turns on TCP session synchronization, so that TCP connections survive a failover event. The set session pickup connectionless enable line extends session sync to UDP and ICMP flows, important for workloads with significant UDP traffic. The set HA management status enable line enables independent management access on the Fortigate, so you can administer either device directly even when it is not the primary. The config HA-MGMT-interfaces sub-block declares which interface provides independent management. Inside, edit 1 creates entry 1. The set interface port 4 line designates port 4 as the management interface, which typically sits in the management subnet. The set gateway 10.0.4.1 line sets the default gateway for management sourced traffic. The next line closes the edit 1 entry, and the end line closes the HA-MGMT-interfaces sub-block itself. The set unicast heartbeat enable line activates unicast FGCP, the cloud-compatible Layer 3 variant of the heartbeat protocol. Without this, the cluster cannot form in GCP because standard Layer 2 FGCP does not work in a GCP VPC. The set unicast-HB-peer IP 10.0.3.11 line sets the peer Fortigate's HA interface IP address. On Fortigate-A, this value is Fortigate-B's HA-NIC IP, and on Fortigate-B it would be reversed to point to Fortigate-A's HA-NIC IP. The set priority 200 line sets this device's election priority. On the intended secondary you would configure this as 100 instead, so the intended primary wins the initial election when both devices come up. The end terminates the HA configuration block and commits the settings. The second block configures the GCP SDN connector. The config system SDN connector command enters the connector configuration context. The edit GCP HA line creates a new connector named GCP HA, which is an administrative label you choose. The set type Google CP line declares this connector as a Google CP connector, as opposed to AWS, Azure, or other supported types. This determines which API endpoints and authentication model the connector uses. The set use metadata IAM enable line tells the connector to retrieve credentials from the Google Cloud Instance metadata service using the attached service account. This is the recommended authentication approach and eliminates any need to store credentials on the Fortigate itself. The set HA status enable line activates the HA-specific behavior of the connector, instructing it to manage routes, external IPs, and alias IPs during failover events. Without this, the connector still works for dynamic object resolution but does not perform HA failover actions. The set GCP project My Project ID line specifies the Google Cloud Project ID where the Fortigate resource is live. The project is the resource container in GCP, and the connector needs this to construct valid API resource paths. The set update interval 60 line sets the dynamic object refresh interval in seconds. The connector polls Google Cloud at this interval to refresh address objects and other dynamic resources. Failover API calls are not affected by this interval. They happen immediately on failover detection. Acceptable values range from 30 to 3600 seconds. The next line terminates the connector entry, and the end line commits the SDN connector configuration. After this configuration is in place on both Fortigates, and the service account attached to each virtual machine has the custom role we defined earlier. The cluster will form and the SDN connector will be ready to handle failover events. You would also pre-create the two GCP VPC routes at priorities 100 and 200, one pointing to each FortiGate, so that the connector has routes to manipulate during failover rather than creating them from scratch. That completes the GCP HA reference architecture, the key mental model that carries across all three clouds. Replace Layer 2 FGCP with Unicast FGCP. Replace gratuitous ARP and MAC failover with Cloud API calls that modify routes and IP assignments, and authenticate those API calls with the cloud's native workload identity mechanism. Only the specific primitives and API shapes change between AWS, Azure, and GCP. Understanding one cloud's pattern gives you 90% of the knowledge needed for the others.